I just want to start by taking the opportunity, taking off what Anya mentioned and Adam mentioned as well. I was here in KIPAC. It was a great time, and I'm happy to be visiting as many of you. And I just want to say thank you and congratulations to KIPAC for the anniversary. And then, as was mentioned before, I'm in the Dark Cosmology Center in the Niels Bohr Institute in the University of Copenhagen. And the work I'm going to talk about here is in collaboration with these people here that we already see Adam talking before, Steve is here, and then there's a bunch of people from Wiggles collaboration and some other collaborators. So what I'm going to talk about here, I'm skipping the title because basically my outline is a little bit paying more attention to the description of the title and some keywords. And this is what I want you to actually, some of these points here I would like for you to take home message after the talk. And it could be actually, as well as the outline, the summary, though the summary will be a little bit different, but I just want to stress the following points. I put in the title, Measuring Cosmic Growth and Cosmic Expansion. And one thing that is important is that we do that simultaneously. We've seen already with the talk of Adam that actually the way that we do the analysis for the galaxy clusters, for example, this is one of the probes that I'm going to use, is actually using simultaneously all the relevant parameters, not only cosmological but astrophysical parameters. And here I'm going to follow in the same line. And what I want to do now is pay attention to two important cosmological quantities, which is cosmic growth and expansion. Normally, cosmic expansion is the one that gets the most of the attention so far with the current cosmological measurements. But my claim here is that now it's the time for cosmic growth with a specific measurement that I'm going to be showing to be put at the same level as the cosmic expansion and to be analyzed at the same time. I'm going to do that by a combination of independent experiments. This is important as well. Just Anya was talking about the relevance of taking care of systematics, and this independent work here, it's related to that. I'm going to use different experiments with each of them take well care of their own systematics, and I'm going to combine them, and this is going to give me a robust result of what I'm looking for. Another important concept that I want to mention here is covariances. As I mentioned, we have astrophysical and cosmological parameters, and we have a lot of them. I'm just going to stress some of them for the relevance of what I'm going to talk here, but all of them are measured at the same time, and they have a lot of covariances. I'm just going to focus on some of these covariances, but all the rest are there, and this is very important for this analysis. And this is not the case normally, as Risa was mentioning in a different context the other day. It's not the case that normally in cosmological analysis nowadays. And I think that this is very important. And then due to paying attention to these covariances, I'm going to pay attention to the degeneracies between parameters, and then I'm going to try to break these degeneracies by combining appropriate measurements. So finally, the theoretical motivation behind that is that we measure cosmic acceleration. That's why we're having this session here. The current standard model, as we heard from the beginning from Lenny as well, is lambda CDM. And we have as well another important piece of this paradigm that is general relativity, that gives us the description for gravity and how the things grow. And this goes linked again to the measuring cosmic growth. And I'm going to do that at larger scales. As you can see here, we have galaxy clusters, CMB, galaxy clusters, all these are large scale probes. We know GR very well at smaller scales and solar system scales, but we are starting to know now only GR at large scales, cosmic scales. So with this preface, I just want to go quickly. So some of the quantities that are going to be important here, I'm going to use two probes of large scale structure, galaxy clusters, and galaxy clustering. And the CMB, of course, it's a little bit different kind of probes. I'll mention a bit later. But in both of these probes, the relevant quantity is the power spectrum, the fluctuations of matter. And there's different parts here, one coming from inflation, one coming from baryon physics, and then there is the growth that comes from gravity. And that's the quantity that I'm interested in for this talk. And this is the evolution of the fluctuations. And this is what I'm interested in is how this quantity changes. That's basically its derivative. And I'm going to describe this derivative. There's a very simple way to describe the derivative, which is with a power law of omega matter, which is the mean density, and this parameter here. So basically now we have a link between this growth and the expansion. If we go to GR, we just can't describe the solution of this, of the evolution of the perturbations with this equation here, but with this way of describing it, we just know that this is a constant value for GR, and for other parameters we'll have some different growth. Okay, and that's just the only thing that I'm interested in. I want to measure growth, and I'm going to measure expansion. I want to see if they're consistent with current data. And this is this quantity here. To measure this quantity, sorry about that. To measure this quantity, we have to measure again growth and expansion. Okay, not only growth, and that's going to be important for what I'm going to say later as well. So again, this is this quantity, and this quantity depends on the variance of the density field at a megaparsecs. Could be another number. This is just a reference number, but that's what is used in the community, sigma 8. And the evolution of sigma 8 is basically evolution of the cosmic growth, and that's we can express it in that way. And from here, I just want you to remember that this exponential decay. So we have basically sigma 8 at redshift 0, which is what we can measure with the local measurements of galaxy clusters, and then they decay sub-100 of tau for the current model. And this we can calculate that with this expression. I just wanted to put it out here. I think it's interesting that this is an analytical expression, even if it's not that simple. And it has some dependencies with gamma and W. But basically, for different values of W, independently of the values of W, more or less, for gamma, a constant value, we can get GR. This is a nice property of these equations as well. But of course, there is a correlation with these parameters, as we'll see later as well. So to do these kind of experiments, as I mentioned, we need the expansion model. So the mean matter density, as I just described. The power spectrum, I just put the equations as well, so linear density perturbations. We need information on the nonlinear structure formation. So for that, if we use the galaxy clusters, we have what we call a halo mass function that was described as well in one of the previous sessions. And this gives us information on nonlinear structure formation. And if we use the galaxy clustering, we have the nonlinear power spectrum as well. We get both from simulations. Okay, so these are important pieces for both calculations. Finally, we can have as well in GR we have the two potentials, the spatial and temporal potentials are equal. In general, this is not the true, as we saw in the talk of Nasib, and we can in principle have a different relation between lensing and dynamical masses. But essentially here, what I'm going to do is test general relativity. So for general relativity, I know all these pieces exactly well. I know how to calculate them. So I'm going to do that, and I'm going to constrain growth and expansion. At the same time, we normally do expansion, as I mentioned before. We do W. Now I'm going to do gamma, which is actually equivalent to W, just as a way to express what happens if we depart from lambda CDM or from GR. They're exactly equivalent. So we should do that because our data allows us to do that. So as I'm going to show now, and they are at the equivalent stage in the moment, which is very interesting. So first of all, this was some years ago. This through the work that Adam described before. One of the papers in the series was we're given this result, which is what I was just mentioning, constraints on, sorry about that, the lambda CDM and GR with CMB and clusters. But then we realize, as I mentioned before, and this is the parameter space, again, growth and expansion. Then they realized, though, that if I'm looking at the growth parameter space, so sigma 8, which remember that is the amplitude, and gamma is the evolution in time, which is what we can measure with our data, there is a strong degeneracy here that we notice that work here, and then we wonder what we can do to break this degeneracy, and that's the next step of the work. And then we realized that there are, well, recently we have measurements of redshift space distortion Alco-Pachinski effect that we're going to use to break this degeneracy here. So basically that's what it is we're going to go and look at the distribution of galaxies, the 2-point statistics when the Halo mass function is the 1-point statistic. And then if there was no gravity, essentially, well, we'll have the distribution of galaxies with the isotropic. But we have gravity, so around the potential wells, galaxies infold, and this means that there is additional redshift to this infold, and then we have distortions in the redshift space, and then we can measure this quantity here, okay, which is, of course, related with gravity, and of course, related with growth, and this at different redshift will be different, and we want to measure that. Of course, though, we can see here that this quantity is together F that I described before and sigma n, so we expect to have some degeneracy here. Okay? And the degeneracy that we expect to have, I'll show you in a minute in the results. And then we have the Alco-Pachinski effect, which is purely expansion effect. This is growth and this is expansion, but they are related because it's also when you measure tangential and radial dimensions in an object, or in this case in a pattern in the distribution of galaxies, then what we have is that if we assume that one model, but the true model is different, then you'll have a distortion due to your assumption, and this is going to be affecting your expansion parameters. Okay, so we have these two information. They are strongly correlated. So here you can see, I'm going to, well, this is just, you can see this effect, the distortion in the power spectrum, and the red lines is the model that includes linear theory and nonlinear theory, as I described before. Look at the scales of K. So, as I said, there's a strong correlation between these two quantities, related with the growth and related to the expansion, and here we can see there's a strong correlation. You can see these numbers close to 1. So what we have is from the Wiggle-Z collaboration, we have 4 redshift described here with constraints on these two quantities here that I've been describing. And then we have a low redshift 1, which only have the growth because the Alco-Pachinski effect, since it's low redshift, is negligible. And then we have as well from SDSS3, from the CMAS BOSS data, we have a similar constraint, but only at 1 redshift, which is similar to the 3rd redshift of the Wiggle-Z, 0.6, and this is 0.57. And then we have as well the Alco-Pachinski effect measured, and here they give as well the correlation with the baryon acoustic oscillations, which is another purely expansion effect, but the correlation is very small as expected, but it is included in the analysis. When I say that I could in baryon acoustic oscillations, it's included, if not. So ISW effect as well, we include the CMB. It's sensitive, the low L's are sensitive to the cosmic growth as well, so we include that. Here is the summary of the 3 measurements, galaxy clusters, galaxy clustering, and the CMB. And these are the results of this new analysis. We have here the following. So for galaxy clustering analysis, we have this large degeneracy here, which is due to the combination of these two quantities f and sigma 8 that I mentioned before. This is for the CMB, okay? The CMB have a constraint on gamma, but is relatively weak, but is the reason why we can't cut out the CMB here. If not, would continue going on in this purely expansion growth parameter space. And then these are the clusters, which are the ones that we expect to have a small degeneracy. And here we can see there is still a little bit of degeneracy, which depends on how well we can constrain the masses, as Adam was describing. But the fact that we can combine these two experiments, you can see that the degeneracy are almost orthogonal, so they cut the degeneracy, the combination, and then we have the third constraint that allows us to say that this is a reverse result. We have three experiments. Two of them are intersecting, and the third one, okay, is completely independent and goes on top with a small degeneracy. So this is important to have not only a small constraints, but to have a robust constraints due to the inclusion of the clusters. Okay. Now here we can see how we peak in the measurements of gamma, how we peak in the measurements of sigma 8 due to the combination, and then just quickly, let me say, if we include, for example, BAO, we can cut this degeneracy a little bit more. It's important to have actually the Alko-Paczynski effect as well in here. Remember, we need as well expansion. This again still is cosmic growth. We can see here the degeneracy that we looking at before and how we cut it, and now we have these tiny constraints here with the combination of the three experiments. And then we can, I'll just skip that. This is interesting what we can do with future redshift space distortion data, but I'll jump that if you ask me, I'll explain a bit more because of the constraints on the time. This is again the growth space, and we can see here that when we add additional expansion data, BAO, supernova, and shoes, we don't see that much of a difference because this is gamma and sigma 8, so it's purely growth. So when we add expansion data, we don't see that much of a difference. But if we look at the other parameter spaces, W and omega matter and H naught, we see a big difference. So the platinum constraints here are smaller than the gold constraints, which are with the three experiments. So we have to remember to look at all the parameters, and so this is important for this reason. So, and just this is again the constraints on the W gamma space that I mentioned before for the different combinations. And here you can see, I showed before, the constraints on this plane, gamma and W, growth and expansion, and how they shrink through the combination. And we can shrink a little bit more, at least in the W, due to these other expansion measurements. And here is just the one-dimensional plots, and you can see, interestingly, growth and expansion at the same time, comparable constraints. Okay, that's interesting to see. So we have everything together, and this I'm just going to leave my summary here. Thank you.
If you're not in a lambda CDM type scenario, presumably because of the existence of dark energy forces, the way that you convert between linear perturbations and clusters is going to be different between different classes of theories. So how do you, I noticed that you sort of said that you had simulations of various theories and so on, but how do you fold the fact you have different classes of theories which convert nonlinearly to different ways into a single constraint?
Right, so basically, remember two things first. So as I mentioned before, so your question is what happens with the nonlinear information or dependence on K. As I mentioned before, this is an initial test which is just on linear theory. So in the same way that is W. So this is equivalent to W. So again, you can see it again as equivalent to W. We measure W and we measure gamma at the same time. W would be affected as well for these cases, right? So this, as you described before, you can have as well clustering dark energy or modifications of gravity and so on. So this is all interesting, but for each case you need to have the right information to constrain these models, and this is interesting, and we're working on that. But this is just the minimal consistency test that we should do anyway, since we have the data, and we should include this information, and we should test not only lambda, but GR all the time. And then if we can do more, of course, we should include more information on that. And of course, there is simulations, and this information is not necessarily easy to include properly, but that's, of course, an interesting thing to look at. Yeah.
Let's thank David again.